Hello, and welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In the last video, we looked at what I referred to as standard methods of the sequences, our array and our list. These were methods that you could call and pass them normal values as arguments. In this video, we're going to look at another set of methods, the higher order methods. Now, we've talked about higher order functions before, very briefly back in the chapter on functions. And in fact, we wrote in the following chapter recursive functions that were higher order. Remember, what it means to be higher order is that these are functions, or in this case methods, that take functions as arguments. And what we saw in the chapter on recursion is that we could make our own functions far more flexible and more powerful by doing this. That is exactly what the people who have written these Scala libraries have done, is that they have put in quite a few methods into the standard library that take arguments which are themselves functions. And it gives you a remarkable amount of power. And so these methods are things that will be very helpful for the way you will solve problems from here on out. So let's look at how we could some of the different methods that we can do here. So we'll run this in the REPL, and I want to make a list of some numbers. Sure, it's not necessarily all that significant what numbers I pick here. And now let's talk about the different types of higher order methods that I can call on that. The first one, in some ways the most basic one, is a method called for each. And for each takes a function that is supposed to be executed on everything. So the simplest thing that I might do on a for each is to pass it print line. Okay. And you can see what that does. It calls print line on each of the elements here. So it printed the 4, and then a 6, and then a 4, and a 3, and a 24, etc. Okay, so this is a very simple usage here. And the for each, in some ways, you can think of as being kind of an imperative approach to doing things. It does stuff. What you put in here for this function really needs to be a statement, because for each doesn't give you anything back. What should matter is the side effects from it. And of course, print line is a very simple function to pass in here. I could put in something more significant. We'll see in just a second. This is not necessarily the ideal way to do what I'm about to do. So what would be another way of, so I've declared a var here called short for total, and it's an int. And so what I want to do is I want to make it so that total is equal to the sum of all of these things. Well, to do that, I can go through and have, for each element, I add it into total. And we go through all the elements, and you'll see that when that executes, doesn't print anything, nothing happens. Technically, it returned unit, and as we've seen, the REPL does not print out anything for unit. But now if we look at tot, it has the value of the sum of all of those things. So for each can be used for basically anything where you want to go through and just execute something for every element. So let's refresh the show nums here and talk about kind of the next set of methods that we have. There's a set of different methods that do kind of selection for you. The most commonly used of these is filter. And in fact, so I would argue that there are we're going to talk about 3 different methods that you are going to use over and over and over again. For each is one of them. And it's probably, it's kind of the third most frequently used in my opinion most time. The The two that you're going to use the most, though, are filter and map. And we'll get to map later. What filter does is it selects elements. So now, something to note here, filter does not change our original collection, in this case our list nums. And remember, lists are immutable, so it absolutely couldn't change the list. Even if this were an array, it wouldn't change it. It just gives us back a new one. Filter takes a function that should return a Boolean. Okay, so what it does is it gives us back all of the elements. It gives us back a new collection of the same type. So when I run it on a list, I'm going to get back a new list that only contains the elements for which the Boolean function is satisfied. So let's say here I want to keep all of the elements that are less than 8. Well, the shorthand way to write that function is underscore less than 8. And you'll see that I get a new list of int, and it has 4, 6, 4, 3. It does not include the 24. It does not include the 8. It includes the 5. 3, 2, 6 does not include the 8, the 9. It includes the other 6. And it does not include the 54. Okay, so that's what filter does. There is a companion to filter called filter not, which you can use if it, if you want to express this as a positive, but only keep the things that for which it is false. Some of the other higher order methods that will select things out for you include drop while. So what if I want to get rid of all of the values at the beginning that are even? Okay, well, I can select for being even by using modulo with the 2. So when you take a value and you modulo 2, if it's even, you get 0. If it's odd, you get 1. And so I want to drop all the elements while I have values that their modulo 2 is equal to 0. And what that does is it just drops off the 4, 6, and the 4, and I get everything after that, because the 3 is odd. And whereas filter, if I were to filter with this condition in here, I would throw out all the odd values. Drop while, and filter keeps them, filter not would throw them out. Drop while only drops the things at the beginning, and the first thing that doesn't satisfy this, it keeps from there on out. The counterpart to drop while, just like we saw that there was in the last video, there was a drop and a take. Well, there's a take while as well, so that you can get the prefix that satisfies something. Another function that can be handy, you don't use it nearly as much as, say, filter, but when you need it, it's very helpful. That is partition. And what partition basically does is it gives you the result of both the filter and the filter not as a tuple. So you can see the return type of partition was a tuple of list int, list int. The first one here is all of the even values, and the second one is all of the odd values. So this is what I got when I called filter on the evens, and this is what I got when I called filter not. And so this could very nicely be used with a val assignment and a pattern match, so that we could create two new variables to hold the evens and the odds. Okay, so when you want both, so if you only want things for which something is true, you would definitely use filter for that. If you only want things for which they're false, you could use filter not, or you could change, in this example, make this a not equal or make it equal to 1. But if you need both, the things for which it's true and the things for which it's false, partition is the way to go for that. There's a number of higher order methods that also run tests on things. What if instead of having all the even elements, I just want to know how many there are? Well, turns out there is a method called count. and you pass it a function. And it counts how many things satisfy that. So there are 10 even numbers. And in fact, we could ask evens that. Note that you could do a count by doing a filter and then looking at the length. That's actually less efficient in many cases because it actually had to build the list. Count doesn't have to build the list and look at its length. It just has to count the elements, to run through there once. If you've done much math, you might have seen the people talk about having a set and you say that there exists something, or for all elements in. In this case, we might want to ask questions like, is there an even or is there an odd number in the list? Well, we can say that with nums exists underscore modulo 2 is equal to 0. That will be true if some value exists in this case. Yes, some value exists. What if I ask, does something exist that's greater than 100? No, false. The opposite of exists is for all. Okay, and so that asks, do all of the things in the sequence satisfy it? Well, in this case, no. There are some odd numbers, so we can't say that all of them are even. However, if we ask, are all of them less than 100? The answer is true. So exists, for all, and counts will just check against a Boolean function, and this is often called a predicate in here, when you pass in a function that evaluates to a Boolean, which is going to be applied to all of the elements. We often refer to it as a predicate. You should also note here that I am making generous use of this underscore syntax. Remember, I could have typed this in using the longer syntax for a function. But it turns out that that in a large fraction of the uses of higher order methods, you have the argument that you're using only appears once, and so you can do this shorthand notation with the underscore. It works really well, and it's often even easier to read. Once you get used to saying something in the place of that underscore, you say, well, this is something less than 100, and that is pretty obvious what that means. What if you want to find things in there? So what if I wanted to figure out where the first odd number is? Well, there is an index where. In the last video, we saw index of, where you can ask, well, where is a particular value? Index where is more flexible because I can say something like, where is the first element of something that is greater than 10? Okay. Where is that? It says it's in index 4. So let's print this back out. 0, 1, 2, 3, 4. Indeed, 24 is greater than 10. So it gave us the index where that happens. There is, just like there was index of and last index of, there's an index where and a last index where. And so what if I wanted to find the last index of an odd number? Well, I would get 11, which happens to be the index of the 9 here. And in fact, we could print it out to verify that. So find and index where and last index where so the index where and the last index where are kind of like the index of, except because you get to pass them a function, they're more flexible. Whereas with index of, you had to know the exact value you were searching for. With index where, I don't. I can search for anything greater than 10 or anything that is odd, which gives me a lot more power and flexibility in there. There is another method called find. And what find is going to do for us is it's going to find the first element. Whereas index where returns the index of the first element, find actually gives you back the first element. So something greater than 10. Now, notice the return type here. Technically, this didn't just give us back the value. It gave us, instead of just an int, it gave us an option of an int. And we'll talk about option in about 2 videos from now. Option is a type that is used for the situation where maybe nothing satisfies it. For example, what happens if I say find the first element that is greater than 100? Well, there isn't one. And so the difference between just returning an int, if find just returned an int, what would it do here? There isn't any int that satisfies this, and nothing that it could return to us would say, oh, it wasn't there. So the option has values of some and none. And we'll come back and look at the things that we can do with option, and we'll refer to find because it's something that gives us that. Now, the other function, the other higher order function or method that you're going to use a lot, I said the first one is filter. Filtering stuff to pull out values that you need, remarkably powerful, remarkably helpful. The other one that you use a lot is a function called map. Okay? And what map does, when I map on a collection, or so on a sequence, what happens is it takes the function and applies it to every element. So a simple example would be if I want to have all of the numbers that are in there, but I want them all doubled. Okay. Well, if you compare this to this, you'll see that what happened is it went through and applied, it gave us back the every element that was in here multiplied by 2, which is, this says map of something multiplied by 2. You should think of map as you want to apply a function to every single element. And in this case, you might not think that that's all that significant, and why do you really want this? And where this will really become handy to us, so actually here would be an example. Let's see, we did looked at zip. Imagine you had a long list of tuples. Okay, so I'm going to make one of these. I'll call it tups, and tuples will be nums.zip of res24. Okay. Now, I have a whole bunch of tuples of int, and what I want to do is I want to know, we'll say these ints are distance from, or are points in the xy plane, and I want to know how far all of these points are from the origin. Well, how could we get that? So I'll make a new variable called dists, and what I want to do is I want to take each one of these tuples here, and I want to apply the distance function to it. So because I'm applying a function to every single element, that is what you should think of as map. And I am going to write this, because each element is a tuple, I'm going to give it a variable name t. I could use the ._1, ._2, but as you know, I prefer to use an assignment, even if it's a little bit longer, because I find it easier to read with the pattern matching. So that line right here is going to pull out the first element and the second element and from the tuple t, and then what I want to return is the simple Cartesian distance, okay, the square root of x squared plus y squared. Close off the curly brace that I opened up here, close off the parentheses, and hit enter, and now we get the distances of all of these points from the origin. Okay, so that's the type of thing that map can be helpful for. Later on, we're going to see case classes, and case classes will hold multiple values in them, much like the tuples would. I guess an even simpler example, though in this case, since I started off with a list of just the first elements, it doesn't. This one doesn't seem as significant. But if these tuples were just given to me, I might say, well, I actually don't want both elements. I only want the first one. And so in order to get that, this was supposed to be tups, not nums. In order to get back to nums from this, to pull out the first element of each one, I can map it to the underscore dot underscore 1. Okay, so map is very handy for pulling out information or to transforming information. Anytime where you're like, oh, I have a whole bunch of things and I need to do something to all of them, that's where you should think of map. In many ways, map and for each are similar. The difference is for each just does stuff and doesn't give you anything back. You wind up using map a lot more because map does something, calculates a value, and gives you back all of those values for all of them. Map has a close relative called flat map. And what flat map, let's make a new, actually, let's do it this way. Okay, so I want, this will be interesting. Not tubes, nums dot map. Now, interesting thing, which kind of winds up being helpful here, is that you can, so let's get an in. Yeah, how about we do this? In dot to char dot to string star in. I'm just going to use a regular map there. Do I have a typo? Line elided for control characters. Nums dot map in rocket in to char to string times in. Am I somehow mistyping this? Okay, well, I'll have to look into that. But as I said at the very beginning, I keep these videos with errors and weird things in them. Now, this gave me back a list of all of these strings. And what I did was I took each number, I converted it to a string, and I multiplied it by that number. So we got 4 4s, 6 6s, 24 24s, etc. Actually, oh, the 54 would have been, that's where we went. In modulo 26 plus a dot to char dot to string. Now I understand why I was having that problem. There we go. Okay. The number 4 does not come out as a nice ASCII value, and so that's why it's saying no, you have all types of control characters in here. I needed to add in the letter A, and I also did the modulo, which I wasn't doing before, but I realized that 54 is not a happy letter of the alphabet. Though if I do this with a capital A, because lowercase comes before caps, I probably get things that aren't too weird. The 54 just jumps into lowercase. The 24 went to a Y. Okay. Now, this is map again. The companion to map is called flat map. And what flat map does is it's the same thing as map, except it assumes that all of the values that are going to come up are themselves sequences, and that they are, instead of being like a list of lists, it's going to give you a single list that contains all of the sublists concatenated together. That's what flat map does. Now, you might look at this and go, well, that wasn't a list of lists here. You're right. It was a list of string. But it turns out that Scala will let you treat a string as a sequence of chars. And so you can call flat map on this, and what you get is a single list that has all of the E's followed by all of the G's, etc. Okay, in that order. The other thing to note here is that this is a test, drop while, drop while is something that we just learned about. It's one of these higher order methods, and you saw that we can call it on a list or an array. We can call it on a string too. And it's just treated as a sequence where the elements are chars, and it turns out that char has a method inside of it called isUpper. So this dropped everything that was upper, that dropped all of the opening uppercase, which happens to be the capital T in this. So that runs you through a brief collection of these higher order methods. We'll look at how we could apply them in some later videos, and we also have some other methods to go through, that things you can do with collections.